Okay, so we're going to take a look at some friction problem solving questions. So let's get started. We've got two problems that we're going to look at. In the first one, we have a car that's skidding to a stop to avoid hitting a deer. The car has a mass of 800 kilograms, which means that its weight is approximately 8,000 newtons, and the coefficient of kinetic friction between the car tires and the surface is 0.3. Now, remember that if the car wheels lock up, they're going to skid, so they're going to slip over the surface of the road. In reality, when you're normally driving a car, the wheels don't skid, they rotate. And so there's actually static friction between the wheels and the road if the car is just driving along. But if you slam on the brakes and it starts to skid and you get those streak marks, then you definitely have kinetic friction in that case. Okay, I've said that up is positive and to the right is positive in this case. So we're going to draw our force diagram, right? We've got our perpendicular surface, our force on the car, which is our normal force. We've got the force of the earth down, and then we've got the force pushing to the car on the right, the parallel to the surface. This is also known as the friction force. However, I'm just writing out what objects are involved in this case. Notice that both of these forces, it's the same objects involved. However, this one is in the perpendicular direction, and we call this our normal force, and this one is in our parallel direction, and we call it our friction force. Okay, so I've moved my force diagram and sketch over here, and now for my equations, we know that my forces in the y direction are balanced, which I've written here, and then we know that my forces in the x direction are unbalanced, which is going to give me the sum of my forces in the x direction. There really should be a small x right there. So I know these two relationships, and then I also know that my friction force is equal to my coefficient of kinetic friction times my normal force. Okay, so let's see here. We've got three unknowns, okay, and two equations. Now, we actually know the value of this. It is 8,000 newtons, and we know that this is 0.3. And so now notice that we've got two different unknowns, and we've got ourselves three equations. So we should be able to solve for our sum of the forces. Okay, actually we have three unknowns. This is unknown, this is unknown, and this is unknown. And we have three equations. We should be able to solve for the sum of the forces. So the first thing I'm going to do is I'm going to solve for the perpendicular force by just solving this equation. It's going to come out to 8,000 newtons, which makes sense, right? It balances this one down here. And then I'm going to plug that into here, and then when I multiply 8,000 times 0.3, that's going to tell me how big the friction force is, and then the friction force winds up being my only force in the x direction, so that's going to give me the sum of my forces. So let's just take a look at that here. So I solved for the normal force, I then plugged it in to find my friction force, and I got that my friction was 2,400 newtons, and then I showed that my only force exerted on the car in the x direction was 2,400 newtons, and it's going to be positive, so that is my sum of the forces, right? Sum of the forces is a synonym for the net force. Okay, so then I take my net force, I divide it by my mass, and I get 2,400 divided by 800, so I get 3 meters per second squared is my acceleration, and it's positive. And if we look at a motion diagram for what's going on, the car is moving to the right, or moving to the left, but it's slowing down. And so my acceleration arrows would be to the right, and that means that the acceleration would be positive, which matches what we got. So this makes sense. Good. In the second problem, we have a girl sledding down a hill. The angle of the hill with the horizontal is theta, and her mass is m. The coefficient of kinetic friction between the surface and her sled is mu sub k. Sorry, that should be mu sub k. And they want us to calculate her acceleration. Okay, so I circled my object of interest. Okay, we're going to look at what objects outside of my circle, right, outside of my system are acting on the sledder. So we know that the earth is pulling down on the sledder. We know that the surface is exerting both a perpendicular force on her and a force backwards on her, the parallel force. The perpendicular one we call the normal force, and that's the force that prevents her from going down into the sled, or into the hill. And then the parallel force is the friction force that's slowing her down. If there wasn't any friction, there'd only be the hill could only exert a force perpendicular to its surface that prevents her from going down into the hill. So I've drawn my force diagram. I've made certain to get my angles correct. And I'm going to then add some dotted lines on here, which are going to show me the direction of my incline and a line perpendicular to my incline. Now, I want to ask, in this direction, in the perpendicular direction, what balances this force? Well, it's some component of the force of the earth on the sledder. Now, if one way to think about finding the component that's going to balance this one is to take a flashlight and imagine what would happen if we were to shine light on this arrow. Okay, it would cast a shadow on this axis right here. The length of that shadow represents my component along this axis. It tells me how much of this force is exerted in the y direction. Okay, I can do the same thing by shining a light and seeing how big my shadow is on this axis right here, and that's going to tell me the size of this force exerted on this axis. Imagine we wanted to do the same with this arrow right here, and we wanted to define how much of it is along this axis and how much of it is along this axis. So we ask ourselves, for this arrow, if I were to shine a light sideways, how long would the shadow be that it cast on this perpendicular axis right here? Okay. Well, it would actually be the same length as this arrow. If I wanted to find how much of this arrow, what the component is along my parallel axis here, I would shine a light down and I would see how much of this arrow, how big is the shadow that's cast on this axis right here. And actually, since the light is shining right down on the point, right, this wouldn't cast a shadow at all. And so there is no component on my parallel axis here. So anyway, this is just a nice way to think about how to find the components of a force on two different axes. Okay, so I've got my force diagram. Okay, I've decided that my y direction and my x direction, it would make sense if they were parallel, if one was perpendicular to the surface and one was parallel to the surface, because we see that this force and this force are going to balance each other. And then if I want to know her acceleration down the hill, I'm just going to sum this force and this force. So it's a lot easier if I just look at the forces in the y direction and make my y direction this way and my x direction this way. All right, so in my y direction, we said that these two forces were going to balance, which I've written here. Notice that this is my y component of the earth on the sled. In the y direction, I also know that this component, since this angle is theta, is just going to be my earth on the sled times the cosine of theta. Okay. In the x direction, I add these forces together. I take my x component of the earth on the sled, which is my green arrow right here, and I subtract from it the hill on the sled in the parallel direction. Okay, I know that this is equal to the earth on the sled times the sine of theta. Okay, and so I've got my equations here. All right, this is the one from the y direction. Here's the one from the x direction that we got. And then here is my formula for friction, right? This is just saying that the normal force times the coefficient of kinetic friction is my frictional force. Okay, so I've got my three equations, and we don't know what this is, we don't know what this is, and we don't know what the sum of the forces is or the net force is. All right, this is a different notation than what you saw in freshman physics. We called it F net in freshman physics, but in our textbook, they use the sum of the forces to represent that. Okay, so we've got our three equations, and now we've got three unknowns, so we should be able to solve for them. Just looking at this, this might actually be pretty straightforward. Here, I can solve for this unknown by just moving this over to the other side, and I'm going to get that is equal to mg cosine theta. I can then take this and substitute it into here, and so I'm going to get that my friction force is this mu k mg cosine theta, because that's what this is equal to. And so now I know what my friction force is, and then I can substitute that into this equation here, and I'll know that my sum of the forces is equal to mg sine theta minus mu k mg cosine theta. So let's just take a look at that. If I solve it, I solve for my normal force by moving that piece over. I'm then going to take my normal force and plug it in to my friction force formula. Okay, and then I get my friction force formula is mu k mg cosine theta. And then I'm going to, now that I know my friction force, I'm just going to put it into my equation from the x direction, and I'm going to see what happens. So I plug it in and I get that. So now that I know that my sum of my forces is equal to all this, so I've solved for it. Great. Okay. I know that my acceleration is the sum of my forces divided by my mass. This is Newton's second law. And I know my sum of the forces, so I'm going to plug that in. I'm then going to divide, and I get that acceleration is equal to g sine theta minus mu k g cosine theta. Right? I can do a little bit of, I can pull out the g, so I get g times the sine of theta minus mu k cosine theta. Okay, and let's see if this makes sense. So if g is 0, so there was no gravity at all acting on this girl, then my acceleration of the girl on the sled should be 0. And that makes sense, because you'd expect if she were at a place where there was no gravity, she wouldn't accelerate down the hill. She would either move at constant velocity or just sit there. Secondly, if she were going down a hill that is at 90 degrees, so it's a straight downhill, my sine theta would be 1 and my cosine theta would be 0. So I would get that her acceleration would be g times 1, or just g, which makes sense, because if she's going down a hill that's completely vertical, she's in free fall. And so the equation works in that case. And then lastly, what would happen if my angle were 0 degrees? Well, sine of theta is 0. Okay. So wait, sine of 0 is 0 in that case. So I get 0, and then minus mu k cosine theta. The cosine of 0 degrees is 0, or is 1 rather. So I get that her acceleration would be equal to negative mu sub k g times g, which would be her acceleration if she were moving along a flat surface and slowing down. Okay, so that's just a quick overview. We had done problems like these two in class, but I wanted you to have a chance to see them again, maybe take some notes on them, and have a chance to watch it again and be able to pause if you ever had a question. So come to class with questions. All right, thank you very much.